Okay, here's lesson 5.4 and 5.5, so graphing linear and non-linear relations. So, okay, first it gives us two examples at the top. Line of best fits can be used either curve of best fit or line of best fit, right? So we looked at that already. Different things in nature, different things in life require either a curve of best fit or a line of best fit. Okay, so problem 1. In pairs, read the instructions on page 169 of your textbook. Use grid paper to draw your frames and record your data in the chart below. Graph your data on the grid provided. Okay, so if you looked at that, you would have seen frame numbers like this, just increasing by 1, from 1 to 6. Number of tiles in the frame, so 1, 5, 9, 13, 17, 21. Okay, so let's graph this. Okay, so I'm just going to count by ones, but skipping one. Okay. I put 7, but it wasn't part of ours. And then, let's see what we can go by. We can go by ones, I guess. No, we'll go, each is 2. So switch, so this is frame number. Put the number sign, and this number of tiles is not really space to write it, but you get what should be there. Let's see, now we can graph it. So when frame number is 1, number of tiles is 1. Frame is 2, tiles is 5. So as you can see, it's in the wrong spot. As you can see, if I connect these, it's a linear relation. Oops. Okay. So we know it's a linear relation. Any trends? Okay, so it's as the frame number increases, number of tiles increase. Rising to the right, it's a linear relation. Okay. Describe how you can use the graph to determine the number of tiles in the frame when you know the frame number. So, I'm not going to write it down, but basically we know we can extrapolate. We can continue this line onwards, and we can use it to find how many tiles are in the frame number. So, we'll see that on our next page, okay? In the 10th frame, you know what, we're not going to use our graph for that, but we can, you know what I'm going to do? I'm going to find the number pattern first, okay? So we can see that, you know, it's increasing by 4 each time, so we know there's going to be 4 in there. Okay? So it's increasing by 4, so it's probably going to be 4 times whatever our frame number is. So if we do 4 times 1, we'd have 4, but how do we get from 4 to 1? We take away 3. 2 times 4 is 8, take away 3 is 5. So we would have found so it's 4 times our number, take away 3. Okay, so how do we do that the 10th frame? 4 times 10, so this is the easiest way. So 4 times 10 is 40, minus 3, 37, 15, so 4 times 15, take away 3. 4 times 15 is 60, minus 3, 57. Okay, so number pattern, the number pattern is the easiest way to figure it out, in my opinion. Okay, problem number 2. A typical North American adult consumes about 200 milligrams of coffee a day. Caffeine has a half-life of about 6 hours. This means that about 6 hours after consumption, half the caffeine remains in the person's body. So after 6 hours, half of it's gone. And it'll keep reducing by half. So if we know every 6 hours, it's cut in half. So half of 200 is 100. Cuts in half again, 50. 25. 12.5. Okay, so that's the half-life. Okay. Now, okay, complete the table. What trends do you see in the data? Okay, it's decreasing. It's not linear, right? Because at first this thing decreases by 100, then 50, then 25. So, non-linear relationship, and we'll see what it looks like. the graph is going to be, it's going to be starting steep and then it's going to level off and curve like that. Okay, so let's see. Hours since consumption. When you do a scatter plot like this, you want to make sure you take up, sorry, I don't know why I count, it's counting by fives, but it should be, we'll do 6, 12, so you make sure you take up most of the graph with your scale, right? If I was doing like, use only this part, it's not going to be, as easy to read. So we want to make sure our scale takes up most of it. Put 0 down here. Amount of caffeine, so sometimes it takes you need to like count it up a bit. So what I can do here, I can 12.5 per one, so each one is going to be 25. Each two, 50, 75, 100. Okay, that works perfectly. Okay, so at 0, we have 200. So starting way at the top. After 6 hours, it's at 100. 12 hours, 50. 18 hours, 25. So you can see, it's kind of what I was saying. It's going to start going down kind of steep, and then it's going to level off. Okay, that'll be our curve best fit. Pretend, you know what? That's a little messed up, but that's okay. I'm not going to erase it and fix it. Describe the graph, so it's a non-linear. It's decreasing. How does the graph compare to predicting part B? I predicted it correctly. How much caffeine will remain after 9 hours? So we can do that two ways. We can say, okay, where's 9 hours in here? It's about halfway between these two. What would we get? Or we can say, okay, 9 hours is between these two. So we can say, okay, what's halfway between these two? Okay, or we can do this, and it's going to be about the same. We can say 75. After 36 hours. So basically we just have to follow this pattern. So if I just want to 6 hours later, this would be cut in half. 6.25, and then 36. Cut that in half. 3.125. Just gonna put 3.13. And then what assumptions have been made? I mean, assumptions meaning, exactly half would go after exactly 6 hours. That's the assumption made. And it might not happen exactly 50%, and it might not happen exactly after 6 hours, and because everyone's different, right? So it might also determine that, or it might rely on how much caffeine you consume in the first place too. So yeah, those are the assumptions. And yeah, that's a quick lesson there. Let me know if you have any questions.